The galaxy known as Thor's Helmet, NGC 2359, is an emission nebula located in the constellation Canis Major, approximately 12,000 light-years from Earth. Although frequently referred to as a galaxy, Thor's Helmet is, in fact, a nebula shaped by the powerful stellar winds emanating from a massive Wolf-Rayet star, WR7, situated at its core. The nebula's striking appearance, reminiscent of the helmet worn by the mythological Norse deity Thor, is the result of complex astrophysical processes involving intense radiation, energetic stellar winds, and expanding gas clouds. NGC 2359 spans about 30 light-years in diameter and exhibits a highly dynamic structure characterized by filaments, shock fronts, and bubble-like cavities. Its distinctive bluish-green color arises primarily from doubly ionized oxygen, OIII, emissions, excited by the ultraviolet radiation emitted by WR7, whose stellar temperature exceeds 50,000 Kelvin. The Wolf-Rayet star at the heart of Thor's helmet represents a rare evolutionary phase of massive stars, characterized by rapid mass loss through strong, radiation-driven stellar winds. Spectroscopic observations have revealed that WR7 continuously ejects material into its surroundings at velocities reaching up to 2,000 kilometers per second. These powerful winds collide with slower-moving gas expelled during earlier stages of stellar evolution, creating shock waves that heat and ionize the surrounding interstellar medium. Over time, the interactions of these stellar winds sculpt the nebula's characteristic shape, forming dense shells and cavities that delineate its intricate morphology. Thor's helmet provides astronomers with a natural laboratory to study the interplay between massive stars and their environments. Infrared and X-ray observations have shown regions of ongoing star formation within the nebula, triggered by shock-induced compression of molecular gas clouds. This phenomenon indicates that massive stars, like WR7, not only influence their immediate surroundings but also play a significant role in shaping star formation processes within their host nebulae. Recent data from space-based observatories, such as the Hubble Space Telescope and Chandra X-ray Observatory, have provided detailed insights into the physical properties of Thor's helmet. High-resolution imagery reveals previously undetected filamentary structures and knots of dense gas, while X-ray emissions highlight hot plasma regions resulting from stellar wind collisions. Furthermore, radio observations contribute additional perspectives on magnetic fields within the nebula, suggesting a significant influence on gas dynamics and morphology. The future evolution of Thor's helmet is closely tied to the fate of its central star. WR7, due to its considerable mass, is expected to end its life as a supernova, a cataclysmic event that will dramatically reshape the nebula and disperse enriched heavy elements throughout the surrounding interstellar medium. Such supernova explosions significantly contribute to cosmic chemical enrichment, influencing subsequent generations of star and planet formation in the Milky Way galaxy. The ongoing study of Thor's helmet nebula thus holds critical implications for understanding stellar evolution, nebular dynamics, and the mechanisms by which massive stars affect galactic ecosystems. Additionally, NGC 2359 serves as an exemplary model for exploring feedback mechanisms within star-forming regions. Massive stars, particularly Wolf-Rayet stars like WR7, inject substantial kinetic energy into their environments through intense stellar winds and radiation pressure. By tracing the energetics and dynamics within Thor's helmet, astronomers can better quantify the influence of these feedback processes on the life cycle of molecular clouds, their fragmentation, and subsequent collapse into protostellar objects. Multi-wavelength studies have underscored the complex chemical interactions within Thor's helmet. Observations in the ultraviolet and infrared wavelengths reveal intricate patterns of molecular hydrogen, H2, and polycyclic aromatic hydrocarbons, PAHs, suggesting active photodissociation and chemical evolution occurring under extreme radiation conditions. Investigating these chemical pathways enriches our understanding of astrochemistry in environments subjected to intense stellar radiation and dynamic physical conditions. Advanced numerical simulations further aid in interpreting observational data, providing theoretical frameworks to analyze how stellar wind-driven bubbles evolve. These computational models highlight the significance of parameters such as ambient gas density, metallicity, stellar mass loss rates, and magnetic fields in shaping nebular morphology. Thor's helmet, with its well-defined structure, offers an ideal testbed for validating these models and refining theoretical predictions about massive star feedback. Furthermore, Thor's helmet also has important implications for understanding galactic-scale processes. Nebulae sculpted by massive stellar activity contribute significantly to the energy budget and chemical evolution of the interstellar medium. The eventual supernova explosion of WR7 is predicted to produce a remnant enriched in heavy elements, such as oxygen, carbon, and iron, elements essential for planetary formation and biological processes. Thus, nebulae like Thor's helmet represent critical links between stellar evolution and galactic chemical enrichment, ultimately influencing the potential for life elsewhere in the galaxy. Continuing research into Thor's helmet is likely to benefit significantly from upcoming observational facilities, including next-generation telescopes such as the James Webb Space Telescope, JWST, and extremely large ground-based observatories. Enhanced resolution and sensitivity across broader spectral ranges will facilitate detailed examination of smaller-scale structures within the nebula, elucidate previously unresolved processes, and provide new insights into star formation triggers induced by massive stellar feedback. In conclusion, NGC 2359, Thor's helmet, is more than just a visually captivating astrophysical object. It serves as a critical astrophysical laboratory for comprehending the complex interactions between massive stars, nebular evolution, and the chemical and energetic dynamics governing the evolution of galaxies. Ongoing and future studies will continue to illuminate these connections, advancing our understanding of the broader cosmic cycle of matter and energy. Moreover, Thor's helmet presents opportunities to investigate the role of magnetic fields in nebular dynamics. Polarimetric studies indicate that magnetic fields permeating NGC 2359 significantly influence gas flow, filament formation, and the propagation of shock fronts. Understanding magnetic interactions within the nebula provides crucial insights into broader astrophysical questions concerning the role of magnetism in stellar evolution and nebular morphology. Astrophysical research into Thor's helmet also yields important constraints on stellar evolutionary models, particularly concerning massive star evolution. Wolf-Rayet stars like WR7 represent short-lived phases in the evolution of massive stars, typically lasting only a few 100,000 years. By precisely characterizing stellar properties, such as mass loss rates, luminosity, surface temperature, and chemical abundances, astronomers refine theoretical models predicting the evolutionary pathways leading toward core collapse supernovae, neutron stars, or black holes. Additionally, Thor's helmet contributes valuable empirical data for calibrating distance measurements across the Milky Way. Precise measurements of nebular expansion velocities, combined with spectroscopic data, enable astronomers to estimate accurate distances and thereby calibrate cosmological and galactic distance scales. This enhances our understanding of galactic structure, particularly in tracing spiral arm features and star-forming regions. Thor's helmet also holds significance in comparative astrophysics. Similar Wolf-Rayet nebulae found throughout the Milky Way, and even in nearby galaxies such as the Large Magellanic Cloud, provide comparative samples allowing astronomers to investigate how environmental conditions, such as metallicity and galactic location, influence stellar feedback processes. Comparative analyses enhance our understanding of star formation across diverse cosmic environments. Recent advances in observational technologies, including adaptive optics, integral field spectroscopy, and high-resolution interferometry, promise to significantly expand knowledge about Thor's helmet. These methodologies allow astronomers to spatially resolve nebular structures and measure subtle kinematic motions within the nebula, providing unprecedented detail into the physical conditions governing star formation processes and nebular dynamics. In a broader context, Thor's helmet exemplifies the intimate relationship between massive stars and cosmic recycling processes. As WR7 sheds enriched stellar material into the surrounding nebula, it actively participates in the galactic recycling of heavy elements. This enrichment influences future stellar generations, affecting the chemical composition of star systems and their planetary bodies. Consequently, studies of NGC 2359 provide critical insights into the cosmic origins of elements essential to life. Thor's helmet thus embodies a key astrophysical laboratory, bridging observational astronomy, theoretical modeling, and numerical simulations. The continued investigation of this nebula will deepen our comprehension of how massive stars sculpt their surroundings, regulate star formation, and drive chemical enrichment processes across galactic timescales. Future observational campaigns directed at Thor's helmet will likely focus on capturing transient phenomena within the nebula. High-cadence monitoring may reveal subtle variations in emission intensities, shockfront propagation, and fluctuations in stellar wind density, illuminating processes occurring on shorter timescales. This can significantly improve theoretical models that currently rely on averaged conditions over extended periods, thereby refining our understanding of stellar wind interactions in dynamically evolving nebulae. Thor's helmet also provides essential data on dust formation and destruction in harsh radiation environments. Observations in infrared and submillimeter wavelengths reveal dust grain populations subjected to continuous erosion by ultraviolet radiation and stellar winds from WR7. Understanding dust survivability and replenishment processes in such environments helps constrain astrophysical models of dust evolution and informs theories related to planetary formation processes occurring in similar energetic environments elsewhere in the universe. Additionally, Thor's helmet can shed light on the astrophysics of turbulence. The nebula's complex internal motions, driven by violent stellar winds and radiative forces, result in turbulent gas flows and interactions that influence nebular structure and star formation efficiency. Detailed spectroscopic mapping of gas velocities across different regions of the nebula enables astronomers to characterize turbulence parameters, providing empirical data essential for testing theoretical predictions related to astrophysical turbulence across multiple cosmic scales. As WR7 approaches its eventual supernova event, Thor's helmet may also serve as a case study for the precursors to stellar explosions. High-resolution spectral monitoring could reveal subtle changes in stellar wind properties, chemical abundances, and radiation signatures in the decades or centuries preceding core collapse. Identifying such precursors would be groundbreaking, offering astronomers potential indicators for predicting supernovae in similar massive star systems throughout our galaxy. Moreover, studies of Thor's helmet enhance our comprehension of feedback loops between star formation and interstellar medium conditions. By elucidating how intense stellar winds alter local gas densities and pressures, researchers can quantify the threshold conditions required to trigger or suppress subsequent generations of star formation. Such analyses have significant implications for understanding galaxy-scale star formation efficiency and the evolution of galactic stellar populations. Collaborations between observational astronomers, theoretical astrophysicists, and computational modelers will play an essential role in advancing our understanding of Thor's helmet. Integrated analyses combining multi-wavelength observations, advanced simulations, and theoretical frameworks will provide the comprehensive perspective necessary to decode complex astrophysical phenomena occurring within and around massive star nebulae. Ultimately, Thor's helmet remains a prime object for advancing key astrophysical questions concerning stellar evolution, nebular dynamics, chemical enrichment processes, and galactic ecology. Continued exploration of this nebula promises not only to enhance our detailed knowledge of its internal astrophysics but also to significantly contribute to broader cosmic theories of matter cycling, star formation, and the ongoing evolution of galaxies throughout the observable universe. Investigations of Thor's helmet also contribute to the broader understanding of high-energy astrophysical phenomena, particularly concerning the origin and propagation of cosmic rays. Massive stars like WR7 are capable of accelerating charged particles within their powerful stellar winds, potentially serving as sources of cosmic rays detectable at Earth. Detailed gamma-ray and X-ray observations of Thor's helmet enable researchers to probe particle acceleration processes and assess the nebula's contribution to galactic cosmic ray populations. Furthermore, Thor's helmet provides insights into the physical conditions and processes occurring at the interfaces between hot ionized gas and dense molecular clouds. These interfaces, known as photodissociation regions, PDRs, exhibit complex chemical reactions driven by energetic photons emitted by WR7. By examining these transition zones through high-resolution spectroscopy, astronomers can characterize the chemical and physical gradients that influence star formation efficiency and molecular cloud evolution within the nebula. Another essential aspect of research into Thor's helmet involves understanding the processes behind the formation of Wolf-Rayet stars themselves. By accurately measuring the stellar properties and evolutionary states of WR7, scientists can constrain models of massive star formation and binary interactions. This has implications for theories predicting the relative frequencies and lifetimes of Wolf-Rayet stars within galaxies, influencing broader interpretations of galactic evolution and chemical enrichment histories. Moreover, the nebula provides an observational benchmark for studying radiation-driven gas dynamics in astrophysical contexts. Observations reveal intricate filamentary structures formed by instabilities driven by intense radiation pressure and stellar wind shocks. Numerical modeling of these instabilities, calibrated against observational data from Thor's helmet, improves our general understanding of radiation hydrodynamic phenomena prevalent in astrophysical objects ranging from planetary nebulae to massive star-forming regions. Thor's helmet also serves as a valuable target for developing advanced astronomical instrumentation and observational techniques. Its relatively bright emission across a wide range of wavelengths, spanning optical, infrared, ultraviolet, and X-ray regimes, offers opportunities for testing and refining imaging and spectroscopic methods, adaptive optics systems, interferometric arrays, and polarimetric instrumentation. Innovations driven by observations of Thor's helmet thus benefit broader astronomical research initiatives. Additionally, the nebula aids studies concerning the life cycle of interstellar bubbles formed by massive stars. By examining how expanding gas bubbles like Thor's helmet interact with their surrounding environments, astronomers gain insights into the physical mechanisms controlling bubble evolution, growth rates, and fragmentation processes. Understanding these processes is essential for accurately modeling the interstellar medium's evolution and its connection to galactic ecology. In the context of exoplanetary science, studying Thor's helmet informs our understanding of planetary habitability around massive stars. Although Wolf-Rayet stars themselves are short-lived in hostile environments, nebulae enriched by their ejecta seed the interstellar medium with complex molecules and heavy elements crucial for planetary formation elsewhere. Analyzing the chemical enrichment occurring within Thor's helmet can shed light on how such processes influence planetary formation and habitability conditions across the galaxy. Ultimately, continued research into Thor's helmet promises multidimensional insights, spanning stellar astrophysics, chemical enrichment, radiation-driven dynamics, and cosmic ecology. Through ongoing observations and modeling efforts, this remarkable astrophysical object continues to provide critical data enhancing our comprehension of the intricate interplay between massive stars and their galactic environments, illuminating the broader cosmic processes governing the universe. Observational advances also increasingly emphasize the three-dimensional characterization of Thor's helmet nebula. By employing spectroscopic tomography and velocity mapping techniques, astronomers reconstruct spatially detailed three-dimensional models of the nebula's structure. These reconstructions significantly enhance our ability to interpret nebular morphology, differentiate between foreground and background gas layers, and accurately trace the propagation of shock waves and turbulent flows originating from WR7's intense stellar winds. Another intriguing research avenue involves studying the effects of binary companions on Wolf-Rayet stars within nebulae like Thor's helmet. Although currently WR7 is classified as a single star, detailed observations continue to probe the possibility of binary interactions influencing its evolution and mass loss properties. Clarifying the role of binary companions in shaping Wolf-Rayet nebulae offers critical insight into the complex processes governing massive stellar evolution and the resulting nebular morphologies. Furthermore, astronomers are now incorporating machine learning and artificial intelligence techniques into their studies of nebulae such as Thor's helmet. These computational approaches enable efficient analysis of massive multi-wavelength datasets, facilitating the identification of subtle patterns and correlations that might otherwise go unnoticed. Such methods can potentially uncover previously unknown structural features, enhance classification accuracy, and streamline comparisons between observational data and theoretical models. Thor's helmet also plays a valuable role in public outreach and education efforts due to its visually captivating appearance. High-resolution images from telescopes such as Hubble, JWST, and ground-based observatories frequently feature this nebula as a compelling example illustrating stellar evolution, the power of stellar winds, and cosmic recycling processes. Thus, scientific research on Thor's helmet also enriches astronomy's broader cultural impact, promoting public understanding of astrophysics and cosmic processes. Ongoing and future research will benefit from continued synergy between observational facilities across the electromagnetic spectrum, spanning radio, infrared, optical, ultraviolet, and X-ray wavelengths. Combining data from telescopes such as ALMA, Hubble, JWST, and Chandra enables comprehensive multi-wavelength characterization of physical conditions within Thor's helmet, such as temperature, density, chemical composition, magnetic fields, and turbulence, providing holistic views into nebular physics. Moreover, as astrophysical simulations continue to advance, Thor's helmet will serve as a critical testbed for verifying and refining computational models that simulate stellar feedback, nebular evolution, and shock interactions. High-performance computational resources now allow astronomers to run sophisticated simulations incorporating magnetic fields, radiation transfer, hydrodynamics, and detailed chemistry, significantly enhancing predictive accuracy regarding nebular evolution scenarios. Finally, Thor's helmet offers valuable data for studies of stellar nucleosynthesis and chemical enrichment. By analyzing the elemental abundances present within the nebula, scientists can directly infer nucleosynthetic processes occurring within massive stars and subsequent contributions to the galactic inventory of elements. Such analyses deepen our understanding of cosmic chemical evolution, element distribution across galaxies, and the astrophysical origins of the elements necessary for planetary systems and life. Ultimately, Thor's helmet remains an astrophysical cornerstone for comprehensively studying the intricate connections between massive stellar evolution, nebular dynamics, chemical enrichment, and galactic ecology, promising continued revelations about the fundamental processes shaping our cosmic environment. Continued investigations of Thor's helmet are increasingly emphasizing the role of radiation transfer modeling to better interpret observations of nebular emission lines. Detailed modeling allows astronomers to accurately derive the physical properties of the gas, such as electron densities, temperatures, and ionization states, from observed spectra. These models are crucial for quantifying the energy budget within the nebula, determining how radiation from WR7 affects gas dynamics, and refining theoretical predictions of nebular expansion rates. Additionally, the nebula offers a unique opportunity to study the process of triggered star formation induced by massive stellar feedback. High-resolution observations have identified regions within Thor's helmet exhibiting signs of recent or ongoing star formation, likely stimulated by shock-induced compression from expanding stellar wind bubbles. By analyzing these star-forming regions in detail, astronomers can measure star formation rates, examine protostellar disk structures, and assess the efficiency of stellar feedback in generating new generations of stars. Thor's helmet is also valuable for testing theories related to instability-driven nebular fragmentation. Observations reveal that gas structures within the nebula are shaped by multiple instabilities, including Rayleigh-Taylor and Kelvin-Helmholtz instabilities, generated at the interfaces between rapidly expanding stellar wind regions and denser gas clouds. Investigating these instabilities provides critical observational data to validate and refine hydrodynamical simulations of gas dynamics, fragmentation processes, and nebular evolution under extreme stellar wind conditions. Furthermore, detailed studies of Thor's helmet nebula contribute significantly to the broader understanding of metallicity variations within massive star environments. Wolf-Rayet stars like WR7 exhibit chemically enriched atmospheres due to advanced nucleosynthesis and heavy mass loss, allowing astronomers to directly measure elemental abundances of carbon, nitrogen, oxygen, and helium. Understanding these elemental distributions within Thor's helmet can provide empirical benchmarks for models predicting metallicity-dependent stellar evolutionary outcomes across galaxies. Thor's helmet is increasingly recognized as an ideal object to study mass loss processes and wind clumping phenomena in Wolf-Rayet stars. Clumping within stellar winds profoundly influences the interpretation of observational data, impacting estimates of stellar mass loss rates, wind velocities, and luminosities. Spectroscopic observations targeting clumping indicators in WR7 stellar wind help refine theoretical mass loss prescriptions, thereby improving evolutionary predictions for massive stars throughout the universe. Upcoming surveys and large-scale observational programs will further enrich our understanding of Thor's helmet. Sky surveys such as the Vera C. Rubin Observatory's Legacy Survey of Space and Time, LSST, may detect variability in nebular emission related to transient stellar wind phenomena or precursor events preceding stellar collapse. Such detections would enhance understanding of massive star variability and contribute valuable information about pre-supernova stages. Finally, Thor's helmet also holds astrophysical relevance for cosmological scale studies of stellar populations and feedback processes in distant galaxies. Nebulae energized by massive stars, analogous to Thor's helmet, are frequently observed at cosmological distances, providing clues about star formation, feedback efficiency, and chemical evolution in early universe galaxies. Thus, detailed local studies of Thor's helmet help interpret and contextualize observations of distant nebulae and inform galaxy evolution models. Overall, the ongoing, multidisciplinary investigation of Thor's helmet nebula continues to bridge observational astronomy, theoretical astrophysics, computational modeling, and cosmological studies. This nebula not only provides a compelling demonstration of stellar feedback processes but also significantly contributes to the broader astrophysical narrative concerning the life cycle of matter, stellar evolution, chemical enrichment, and the evolution of galaxies across cosmic time. Future studies involving Thor's helmet will benefit greatly from developments in space-based ultraviolet astronomy. By leveraging future UV missions, astronomers can obtain precise measurements of stellar radiation fields and ionization structures within the nebula. UV observations are particularly critical for accurately determining abundances of elements like carbon, nitrogen, and oxygen, key tracers of nucleosynthetic processes and stellar evolution pathways, within the nebula's hot, ionized gas. Additionally, Thor's helmet will likely play an integral role in improving our understanding of Wolf-Rayet stars as progenitors of gamma-ray bursts, GRBs. Although the specific evolutionary path leading Wolf-Rayet stars to GRB explosions remains an active area of research, nebulae like Thor's helmet provide observational data to constrain theoretical models linking massive star evolution to GRB progenitor scenarios. Identifying unique spectroscopic or morphological signatures associated with potential GRB progenitors is an exciting avenue for future astrophysical research. Furthermore, advances in polarization studies promise insights into magnetic field alignment, strength, and orientation within Thor's helmet. Polarimetric observations in optical and infrared wavelengths can help astronomers characterize the influence of magnetic fields on nebular shaping, turbulence, and star formation processes. Understanding these magnetic influences is fundamental for comprehensive models of star-forming regions and feedback mechanisms involving massive stars. Thor's helmet also represents a key observational target for examining interactions between stellar ejecta and previously expelled circumstellar material. Such interactions create distinctive spectroscopic signatures and complex morphological structures. Detailed studies of these interactions could significantly enhance predictions about late-stage stellar evolution phenomena, mass loss history reconstructions, and the characterization of circumstellar environments around massive stars. Observations of Thor's helmet at high angular resolution using interferometry, particularly with radio and submillimeter telescopes such as ALMA or future arrays, could resolve previously unexplored small-scale structures within the nebula. These observations would reveal intricate details regarding molecular gas distribution, dust grain properties, and chemical gradients within the nebula. Such data is essential for a nuanced understanding of nebular chemistry and the effects of stellar feedback on molecular cloud evolution. Computational astrophysics will continue to play a crucial role in interpreting and guiding observations of Thor's helmet. Future generations of hydrodynamical simulations, incorporating sophisticated radiative transfer, chemical networks, and detailed stellar evolution models, will enable astronomers to predict observable features more accurately. These simulations also offer powerful tools for hypothesis testing and refining theories concerning massive stellar feedback and nebular dynamics. Additionally, the nebula provides important data for understanding how stellar feedback influences the interstellar medium, ISM, on both local and galactic scales. Observations of Thor's helmet inform ISM models regarding energy injection, turbulence generation, and shock-driven star formation, which collectively govern galaxy-scale evolution processes, including gas recycling, star formation efficiency, and chemical enrichment. Ultimately, Thor's helmet remains an exceptional astrophysical laboratory for advancing the scientific understanding of stellar evolution, nebular astrophysics, star formation, and galactic ecology. Continuous observational, theoretical, and computational studies of this intriguing nebula promise enduring contributions to astrophysics, enabling significant advancements in our grasp of fundamental cosmic processes and their intricate interconnections throughout the universe. Beyond its direct contributions to stellar and nebular astrophysics, Thor's helmet also serves as a key reference point in the study of feedback-regulated galactic ecosystems. As massive stars like WR7 inject momentum, energy, and enriched material into their surroundings, they drive the formation of superbubbles, larger, interconnected cavities formed by overlapping stellar winds and supernovae. Thor's helmet is considered a microcosm of this larger-scale phenomenon, offering astronomers the opportunity to observe, in exquisite detail, the processes that shape entire regions of galactic interstellar medium. These feedback processes are not merely disruptive, they are constructive as well. The compression of molecular clouds by expanding shock fronts can lead to the gravitational collapse of gas and the formation of new stars. In this way, the death throes of one generation of stars become the cradle of the next. Thor's helmet encapsulates this duality, embodying both stellar destruction and rebirth, a self-regulating system of cosmic renewal. This makes it an ideal site to study how galaxies maintain equilibrium over time between star formation and the dispersal of star-forming material. From a chemical perspective, ongoing spectroscopic studies of Thor's helmet refine our understanding of nucleosynthesis signatures in Wolf-Rayet ejecta. By mapping the spatial distribution of elements such as helium, nitrogen, carbon, and oxygen, researchers can reconstruct the sequence of fusion processes that occurred deep within WR7 before its outer layers were expelled. This forensic approach to stellar chemistry allows scientists to connect the final stages of stellar life with the broader chemical makeup of galaxies. The nebula is also becoming a touchstone in the study of time-domain astrophysics. Though it may appear static on human timescales, subtle changes in emission line strengths, bubble expansion rates, and dust morphology can occur over decades. Long-term monitoring of Thor's helmet allows for the detection of such gradual transformations, turning the nebula into a real-time laboratory for observing the slow choreography of cosmic evolution. These subtle temporal variations offer rare opportunities to study the dynamic processes of stellar wind interaction, cooling flows, and radiative transfer within an active nebular structure. Thor's helmet is additionally significant in the context of gravitational wave astrophysics. As our ability to detect gravitational waves from massive stellar mergers improves, regions like NGC 2359 become increasingly valuable for identifying likely progenitor systems. While WR7 itself may not be in a binary system capable of producing detectable gravitational waves, studying similar nebulae helps build a statistical understanding of the environments and life cycles leading up to such events. This provides crucial environmental context for interpreting gravitational wave signals from distant parts of the cosmos. In educational and cultural contexts, Thor's helmet holds symbolic and aesthetic appeal. Its mythological name and striking visual resemblance to a warrior's helmet invite public imagination, bridging the gap between science and storytelling. It becomes not just a subject of academic inquiry, but a cosmic icon, embodying the fierce elegance of stellar life and death, and serving as a reminder of our connection to the stars. Educational programs and visualizations built around Thor's helmet continue to inspire new generations of astronomers and science enthusiasts. In the years to come, as new space observatories such as the Nancy Grace Roman Space Telescope and LUVOIR, large UV/optical/IR surveyor, come online, Thor's helmet will undoubtedly remain a key observational target. These next-generation telescopes will enable even finer analyses of its ionized gas structures, dust physics, and embedded stellar populations. With each advance in technology, Thor's helmet will reveal more of its secrets, both confirming long-standing theories and challenging others, while anchoring our understanding of massive stellar evolution within the broader narrative of cosmic history. As the frontier of astrophysical exploration advances, Thor's helmet stands as a dynamic canvas where emerging technologies and interdisciplinary approaches converge. One promising direction lies in the integration of astrochemistry and radiative hydrodynamics, offering a more nuanced perspective on how molecules form, evolve, and survive in the presence of harsh radiation fields. Within NGC 2359, the intense ultraviolet flux from WR7 creates stratified zones of ionization, dissociation, and recombination, each with unique chemical signatures. Detailed modeling of these stratified layers, when compared against observations in the mid-infrared and sub-millimeter ranges, can illuminate the pathways by which complex molecules either form or are destroyed in nebular environments shaped by massive stars. Such studies are particularly relevant for understanding the preconditions for life elsewhere in the universe. While Thor's helmet is far from habitable, the elemental enrichment and molecular chemistry within its structure offer a glimpse into how organic precursors may be disseminated into space by evolved stars. This connects local astrophysical phenomena with astrobiological inquiry, linking stellar death with the seeding of planets and potentially life-bearing environments elsewhere in the galaxy. At the same time, improvements in 3D spectroscopic mapping, especially with instruments like MUSE on the Very Large Telescope, VLT, are allowing astronomers to unravel the velocity structure of the nebula in exceptional detail. Each spire, filament, and arc becomes a vector in a vast dynamical system, shaped by the interplay of explosive outflows, radiation pressure, and magnetohydrodynamic instabilities. These 3D maps are key to testing numerical simulations, validating predictions of flow patterns, shock propagation, and the diffusion of chemical elements through turbulent plasma. As simulations increase in realism and resolution, observations of Thor's helmet serve as ground truth for modeling feedback-regulated star formation in complex, nonlinear environments. Another exciting frontier is the exploration of polarization in scattered light from dust grains within the nebula. Polarimetric imaging can reveal the orientation and coherence of magnetic fields on subparsec scales, offering clues to the magnetic history of the gas and dust shaped by WR7's wind. When cross-referenced with velocity fields and ionization structures, these measurements may help answer enduring questions about how magnetic fields influence mass ejection geometry, nebular shaping, and gas confinement in high-energy environments. As Thor's helmet continues its slow evolution, it may even offer the rare opportunity to catch pre-supernova variability or signatures of terminal instability in WR7. The final decades of a massive star's life are thought to be marked by increasing instability, shell ejections, and enhanced mass loss, sometimes detectable as changes in spectral profiles or luminosity. A detection of such pre-collapse activity within Thor's helmet would be groundbreaking, allowing astronomers to witness, and perhaps even predict, the moment when a star crosses the threshold into supernova. If such an event were to occur, it would reshape not only the nebula, but also our understanding of massive stellar death. In essence, Thor's helmet is more than a relic of stellar evolution, it is an active, breathing structure, molded by the continuous interplay of forces at cosmic scales. It offers astronomers a unique vantage point on a phenomenon that is both ancient and ongoing, the recycling of matter through cycles of stellar life, death, and rebirth. Every photon that escapes its glowing filaments carries a message from deep time, encoded in wavelengths that speak of gravity, thermonuclear fusion, atomic transformation, and cosmic memory. In the endless story written in the stars, Thor's helmet is a chapter that binds past and future. It speaks of destruction and creation in equal measure, of chaos sculpted into beauty, and of a universe in motion, forever weaving new worlds from the ashes of the old. As our instruments grow more sensitive and our models more sophisticated, Thor's helmet is poised to become a central touchstone for unraveling the complexities of feedback-driven cosmic architecture. It exists at the crossroads of multiple disciplines: plasma physics, thermodynamics, radiation transport, turbulence theory, chemical kinetics, and gravitational dynamics, all of which must be interwoven to construct a complete and truthful portrait of its nature. Each arc and plume in the nebula is a frozen expression of forces once unleashed at unimaginable scales, shaped by the internal engines of a dying star and etched into space like a celestial fresco. Future missions dedicated to time-domain astronomy may eventually monitor real-time evolution of WR7's wind patterns, tracing how even minor fluctuations ripple through the surrounding gas like gravitational tides in miniature. The feedback from WR7, though only one star, carries enough power to carve cavities dozens of light-years across, demonstrating how a single massive object can impose order, motion, and chemical complexity on entire regions of the interstellar medium. This stellar authority echoes the influence of quasars and galactic nuclei on vastly larger scales, revealing a fractal pattern of energetic dominance that repeats from star-forming regions to galaxy clusters. Thor's helmet also continues to challenge the limits of observational creativity. Scientists now use synthetic observations, renderings of simulated nebulae translated into virtual telescope data, to compare theory with reality in new ways. By inputting the known properties of WR7 into computational fluid dynamics models and generating light spectra as they would be observed from Earth, researchers can directly confront the successes and failures of our understanding. Thor's helmet, with its wealth of multi-wavelength observations and high spatial detail, is an ideal candidate for such deep verification. The nebula's glowing arcs and turbulent halos may also harbor fossil records of earlier evolutionary phases, traces of slower, cooler winds emitted when WR7 was a red supergiant or luminous blue variable. These concentric, nested shells, if detected, would offer rare windows into the star's pre-Wolf-Rayet history. Like tree rings marking years of growth, the nebular layers may store a timeline of eruptive change and increasing instability, chronicling the long countdown toward supernova in swirling clouds of gas and dust. And still, the symbolism of Thor's helmet extends beyond the data. Named for the mythic hammer-wielding god of thunder, the nebula lives up to its namesake, echoing with invisible thunderclaps of radiation, shaped by cosmic tempests, armored in arcs of oxygen and helium, crowned with a silhouette of myth made manifest in interstellar fire. Its aesthetic resonance reminds us that science and myth are not opposed, but rather entwined in their desire to name and know the heavens. For now, WR7 remains silent in its core, a ticking clock of fusion, burning at unimaginable temperatures, hidden beneath layers of stellar atmosphere. But one day, it will collapse. In a single, incandescent moment, the heart of Thor's helmet will give way, triggering a supernova that will outshine its entire region for weeks or months. When that time comes, whether in years or millennia, observers across Earth and beyond will turn their eyes toward Canis Major to witness the transformation of this nebula from a portrait of stellar life into a sculpture of stellar death. And in that flash, we will read the last word of a stellar story begun millions of years ago, when gravity first pressed hydrogen into light. Until then, Thor's helmet remains a gateway, into the physics of stars, into the history of galaxies, into the nature of time, and into the poetry of the cosmos itself. Thus, Thor's helmet is not merely an astronomical object catalogued among countless nebulae in the night sky, it is a profound embodiment of the cycles that govern our universe. It stands as a cosmic monument to impermanence and transformation, sculpted by forces that simultaneously create and destroy. In its luminous folds, we see the fingerprints of radiation, the echoes of ancient fusion, and the seeds of stars yet to form. It is the visible breath of a dying titan, a nebula where physics becomes form and time becomes structure. In the centuries to come, long after our present-day instruments have been surpassed by technologies we have yet to imagine, Thor's helmet will remain a vital source of astrophysical insight. It will be revisited, re-examined, reinterpreted, as all great cosmic laboratories are, through the lenses of new theories and more precise measurements. Perhaps one day, we will witness its transformation in real time, catching the flash of WR7's death as it collapses into a neutron star or black hole, sending ripples through the fabric of spacetime. Perhaps we will trace the debris field from that supernova for generations, watching as its remnants seed new molecular clouds, new stars, and eventually new planetary systems. And even if that moment lies far beyond our lifetimes, the story told by Thor's helmet continues. Every photon it emits carries with it the memory of ancient reactions and the future potential of matter recycled through stars. Every arc of glowing gas is both a remnant and a promise, proof that nothing in the universe truly ends, but instead changes form, contributes, and re-emerges as something new. In this way, Thor's helmet teaches us not only about the universe, but also about ourselves. It invites us to reflect on the interconnectedness of all things, the way stellar death begets planetary birth, the way violent endings forge elements that one day become oceans, air, and living cells. It reminds us that beauty often arises from chaos, and that within even the most destructive processes, there is creativity, order, and renewal. To study Thor's helmet is to glimpse a piece of the cosmic tapestry, to read a chapter in the endless story of energy, matter, and time. It is a story still unfolding, and one in which we, too, are participants. We are born of the elements forged in stars like WR7, and we carry within us the same atoms that once drifted through glowing nebulae. In the end, Thor's helmet is not just out there. It is within us, around us, and above us, a brilliant reminder of our origin in the stars, our place in the universe, and our unending quest to understand the cosmos that gave us life.